me to this international webinar series. First of all, it's a very nice initiative, Professor Reddy, and I'm happy to contribute with the little knowledge I have. Good morning, good afternoon, good evening to everyone. Today, I will talk about landslide mitigation of urbanized slopes for sustainable growth. After this nice introduction of me by Professor Reddy, I don't think I should say much more about me, but I can say a few words about the university I come from. I did my PhD from this university called Norwegian University of Science and Technology. It has 44,000 students, bachelor and master students, offers 330 study programs, and have over 5,000 courses for professionals. And the university educates more than 70% of master's candidates in technology in Norway. It might not sound very big university in many parts of the world, but with total 44,000 students and around 7,000 staff members, we are approximately 1% of Norway's population. So it's quite big university in Norwegian context, and we are the largest university. In terms of research, so we are around 3,000 professors, associate professors, and over 2,700 PhDs are active at the moment. On average, every year, around 400 PhDs are awarded. We are very much active towards European projects as well as publications. And the university has around 45 national research centers. University also has some world-leading environment. Among others, there's one group who has received Nobel Prize a few years ago in medicine, Kavli Research Institute, by two professors, Moser and Moser. So this was brief about the university. Before I go further, I can just say that I had 20 hours of travel from Singapore, and I just came 1 hour before, checked in the hotel, and I'm very happy that my flight was not delayed. And I will do my best to keep myself awake the next 1 hour. And given the topic for this seminar is sustainability, so I thought to mention this as well. In university, our university, NTNU, has a lot of focus towards SDGs, Sustainable Development Goals. And we have gone as far as to revise our all study programs to include sustainability competence in our study programs, including civil engineering programs. So we will revise our civil engineering program so that we can get SDGs very explicitly visible in the course content and curriculum. The format of my presentation today is this. I will start with very wide background starting from construction sector and climate challenges and so forth, especially focused towards landslide, climate-triggered landslide, water-triggered landslide. Thereafter, I will focus on recent advancements that has taken place in Norway in relation to the assessment and management of water-triggered landslide. I go specifically towards water-triggered landslide because due to changing climate, we have several extreme weather events, and most of landslides are due to high-intensity rainfall or floods. And in that part, I will cover 3 areas. First, I'll talk about structural countermeasures. What are the latest development we have made in terms of structural countermeasures? Thereafter, I will talk about non-structural countermeasure with focus on early warning systems. And third will be risk communication by gamification. And finally, I will have some overarching summary. There could be so that some of the results I will show, they are sort of abstract research results, and it could be difficult to follow at a time. So do not hesitate asking me a question at the end, or else contacting me directly by email or through WhatsApp. You have both information available in this presentation slide. So let's get going with background. And I think it's good to start with our domain. Our domain is civil engineering domain, where geotechnical engineering belongs to. or more specifically, let's say, construction industry. Of course, geotechnics has different applications, but if we limit ourselves to construction industry, so what is the importance of our sector? Construction industry creates approximately 7% jobs worldwide. It is responsible for 10% of GDP, but it also consumes 17% of fresh water due to different construction activities. We are responsible for almost 30% of energy consumption and approximately 40% of CO2 emission. We use almost half of the raw materials available on this planet, and land harvesting is almost around 60%. So we usually call our sector as a 40% sector. Construction sector is called 40% sector because it is responsible for almost 40% energy consumption, CO2 emission, use of raw materials, and so forth. So we can also call it we are 40% of the problem we are facing the construction industry. The good news is that we have 40% of solution as well to create a low emission society by 2050 or 2060. This can be done by adopting circular economy, smart materials, waste management, and getting green shift in the built environment, and also creating resilient infrastructure. So though our sector is responsible for large amount of CO2 emission, I think we are also 40% of the solution. And this is something we need to emphasize on different arenas. However, we have already emitted enough greenhouse gases in the atmosphere, and we have already started to see the consequences in the form of extreme weather. Flood and landslides are becoming quite common. This is one video from Norway, a result of one high-intensity rain that took place some years ago. I will say the future is already here. There was a time when we talked about that climate change will cause extreme weather events and so forth, but I feel that it's already here. And what we see, extreme weather events in terms of flooding and flood-induced landslides and destruction of infrastructure is happening worldwide, and it's putting built environments such as buildings, roads, railways, bridges, tunnels, or nature, and also lives at risk. So future is here. We see already the impact of climate change all around the globe. This is another slide just to illustrate what has happened recently in Norway. Extreme weather event Hans took place. And on the left side, you see map of Norway. It's half of the Norway was pretty much shut down. The main all highways were blocked due to landslides. And the right side, you see some images which is showing destruction of the houses due to debris flows, and roads were destroyed, roads were blocked, buildings were destroyed, and so forth. So it leads to societal safety. How safe are we? And do we have infrastructure who are resilient enough to handle the climate effect we see now? Then I would like to refer to this tweet from UNISDR, which said nearly 87% of disaster-related spending goes on response, reconstruction, and rehabilitation, and only 13% goes towards managing the risk which are driving these disasters in the first place. This imbalance has to be corrected. And I think this fits very well to the current scenario. I think we spend tremendous amount of resources to respond, reconstruct, and rehabilitate after damages are done, whereas a limited amount of resources are available to, in fact, work on developing resilient infrastructure and making society even more safer. As we talk about sustainable development, so I must say that societal safety is the prerequisite for sustainable growth and sustainable development. And in this aspect, geoscientists have a very important role to play in terms of climate-related extreme weather events. So more specifically, let's go towards landslides. So how can we meet the challenges induced by landslides? First of all, I personally believe that multidisciplinarity is the key when we work on landslides. There are meteorologists, hydrologists, hydraulic engineers, geologists, geotechnical engineers, psychologists, all are working with natural hazards from different dimensions. But now we have to come together, work together, because the problem is so complex and huge. It is not up to one domain to be able to solve this particular problem. Of course, we need to think about mitigation measures, which is an engineering challenge, how to make resilient infrastructure, how to make structural countermeasures which are capable of handling large landslide events. But also preparedness is equally important, because the way natural hazards are handled at county level, state level, or federal level, there's some challenges in terms of how preparedness is organized, how we communicate risk, and how we manage risk. I will briefly go through all these three in my presentation through some recent developments we have made. And whatever I'll present here are basically some selected results from a center which we recently executed. It's called Center for Research-Based Innovation, Climate 2050, and other research activities at NTNU. This research center was a national center where NTNU, together with SINTEF, Business School in Norway, Meteorological Institute, NGI, together with public and private partners, did a tremendous amount of work related to climate adaptation, where natural hazard, water-triggered landslide was one of the key areas. In addition, there has been several other ongoing research, several other projects at NTNU, where 6 different PhDs have been working along with more than 30 master students. Also, a couple of professors, associate professors have been part of the team in doing this research. So I'll present summary of some selected results conducted by some of the PhDs at NTNU. And my focus will be towards water-triggered landslide, either it's a soil slide or debris flow. And I will start with structural countermeasures. When we talk about structural countermeasures, there exist more than 70 types of structural countermeasures already. Those countermeasures are useful depending on landslide types, material types, velocity, individual landslides. And some countermeasures are meant to stop the landslide mobility completely. Some are meant to reduce the mobility by dissipating energy. Some are meant to channelize, guide the landslide mass to a certain direction. So depending on the purpose, we choose countermeasure. What I will focus now is towards debris flow countermeasures. Debris flows are becoming very common phenomena in Norway due to excessive rainfall. Basically, debris flows are very rapid to extreme rapid flow of fluidized non-plastic soil water mixture. One typical challenge which we have with debris flow dynamic is that it gets significantly affected by entrainment, meaning that debris flow starts very small and its volume increases, and that may lead to longer runout, high impact forces on infrastructure. So why does this entrainment occur? Entrainment occurs when a debris flow shears a soil bed and generates excess pore pressure, which reduces the shear resistance of bed. In simple words, entrainment is a process where a debris flow or soil mass, when it goes downhill, it collects more material on the way it goes downhill. As you see on the figure to the right, it's a release area 2,000 cubic meters. It's a photo of a debris flow event where initial slide was around 2,000 cubic meter, and the total deposit was up to 10 times more, 20,000 cubic meter in the depositional area. Because as the debris flow propagated downhill, it collected more material and it became larger and larger, just like snow avalanches. So in debris flow, this is one of the biggest challenge is entrainment, how to manage entrainment, and it affects the design of structural countermeasures. So what is a typical countermeasure we use in Norway? It's a terminal wall. As you see, a simple terminal wall that has been used in Norway in many parts of the world, and it does not account for entrainment or flow volume growth. So how can we mitigate debris flow and reduce entrainment? So the recently 2 PhDs were conducted on this topic to study debris flow countermeasure accounting for bed entrainment. One PhD study was related to investigation of a screen structure for mitigating debris flow along coastal roads, and second one was related to flexible barriers. I will present some results from these two work. They have made some publications, and these publications can be referred to get more information. The first work was related to screen structure. The idea using screen was conceived in Japan with the intention to reduce energy in debris flows and thus contribute to mitigating damage in downstream area. The main purpose of this screen is to separate water or the fluid from the moving debris. As a result, poor water pressure develops inside the debris flow, particularly in the shearing zone, to dissipate. In return, debris solid particles regain their contact friction, thereby increasing the shearing resistance of moving debris. So basically, screens are very simple structure with some grates, which has some opening in between. So once debris passes on top of them, it allows water to seep through as well as also dissipate excess pore pressure and pore pressure as well. In doing so, we increase the interparticle contact and therefore debris slows down and in fact stops. We studied this at the lab, about 10-meter long flume, where 6-meter flume was, just 1 second, I'll get a pointer. It's a flume which has a 6-meter long runout channel and 4-meter depositional area. The flume was instrumented with various type of sensors to measure sensor flow heights, pore water pressure at the base. We recorded videos of using high-speed cameras, and different measurements were made using sensor techniques. This is how the flume model looks like. Here is the runout channel, and here is one debris flow screen which was placed, and the flume was 60 centimeters in width. Various number of tests were done by changing the length and the size of the screen, and also by changing the concentration of solid fluid mixture. I will show you one result if I am able to show you. Here you see moving debris on the debris flow screen. As you will see that debris moves on top of it. Eventually, you will see some water will start to seep through the screen, and in doing so, intergranular contacts will increase, and slowly you'll see solid materials will pile up on top of this screen. It is worth mentioning that such kind of countermeasures will not necessarily completely stop the movement of debris flow, but it will significantly reduce the velocity, and thereby the impact caused by debris flow will reduce significantly. So we studied the impact as well, and here you'll see this vertical pillar where we were measuring the impact of a moving debris, and quite many tests were done, and we can see that impact forces were reduced as we used screen type countermeasure. You see some results on the figure to the lower left side, that impact force is reducing. So there was some promising results. Yes, this kind of screen may work despite it doesn't stop debris flow completely. Here you saw the same video on real time. The left one was without countermeasure, as you will see material just runs through. On the right side, you will see the debris, that how quickly material stops on the top of debris screen. All these tests are done in the lab, and the lab has one very big disadvantage when we study debris flow, and that is scaling effect, especially with small models such as this. So upscaling is always important, and to do so, we have to go for numerical simulations or sufficiently large model test. At that time, we did not have very large fume, so we decided to go for numerical modeling, and that was done using GeoFlow SPH FD numerical model developed by the Madrid group and Manuel Pastor. This SPH stands for spherical particle hydrodynamics, finite difference numerical model. The model is suitable for modeling debris flow screen because it is able to simulate the effect of permeable surface, like a screen in which their purpose is to drain water and dissipate pore pressure in the flowing body. The formulations rheology of the model can be obtained from one of the papers which was published recently in Geotechnique. Here you see three numerical simulations done for the real case, where we placed one debris flow screen in the upstream side of the debris flow, as you see here in the yellow circle. Middle image is with the 2 debris flow screen, and third is a 3 debris flow screen, as you see. And depending on how large debris flow screens we place, either we are able to reduce the mobility of a debris flow or we can stop it completely. In 3 debris flow screens, we are able to stop the debris flow completely, not coming all the way down to the road, which is somewhere down here. So in summary, the debris flow screen were able to slow down the mobility of flow mass. And the main purpose of countermeasure was to dissipate pore pressure by filtering out the fluid part from debris flow. The numerical simulations done with using this GeoFlow model gave quite promising results. It was able to replicate runout distance, flow heights, and deposition height, flow velocities, etc. So results are quite promising. However, there are some practical challenges. How to install this kind of screen and maintain them, especially in steep terrain, will be very challenging. It will not be easy to install them. Perhaps it is more suited for flatter or mild sloping terrain, not for very steep terrain. So we started to look for what are the other options to reduce entrainment of solid mass on steeper terrain. And that brought us to upstream flexible barrier system, the second PhD work. Over recent decades, flexible barriers have been increasingly used to mitigate debris flow hazards. Entrainment, the effect of flow barrier interaction needed to be elucidated. One of the design function of installing multiple flexible barrier in channel is to reduce bed entrainment. However, there is a dearth of literature on the use of flexible barriers for controlling channel bed entrainment. Instead, the emphasis of existing work in the literature on impact dynamic is placed on non-erodible bed to improve mitigation measures for controlling. So there are some scientific challenges, especially in terms of understanding bed entrainment because of poor predictability of where actually debris flow may take place, but also the scaling effect that may take place if you use very small flume test. So what we did is we actually did a large-scale flume test, and that was done in Hong Kong. The model which was developed by Professor Charles W.W.Ng, it was used to minimize scaling effect. We wanted to measure flow parameters in entrainment and also the influence of flexible barriers on entrainment. This 28-meter long flume was utilized where almost there was a 7-meter fixed bed. We placed one upstream flexible barrier on the upstream side. We made approximately 6-meter long erodible bed, and also we had a terminal bed at the end. We could use up to 10 cubic meter of debris flow material, 6 to 10 cubic meter of debris flow material in the test. Various measurements were made using some erosion measurement technique. I'll come back to this, but also we are measuring the normal stresses and shear stresses to understand the basal stresses at the base of debris flow by using cell 1 in the upstream side and cell 2 where we wanted to have entrainment. Flexible barriers look something like this. The upstream flexible barrier was just 60 centimeter tall, whereas the terminal flexible barrier where mass is supposed to stop at the end is 1.5 meter height. To understand entrainment, we developed something called erosion column, a very simple technique where we took 5 millimeter high nuts and we installed them using a bolt in the model, just as you see here, E1, E2, E3, E4, E5. If you see E1, for example, so this is how the structure looks like. So the nuts were placed, we use a bolt. After having this setup, we place the erodible bed around it. And thereafter, we removed the bolt so that we had this nuts standing in a form of pillar. So whenever we did the model testing, And whenever erosion took place, it also removed some nuts, and through which we knew how much material has been eroded or entrained. The height of these nuts were 5 millimeters. We did 3 major tests. It's written here, test ID, V2.5 B1, V6 B1, and V6 B2. Volume 2.5 cubic meter with single flexible barrier with a terminal barrier. And then we had 2 other tests with 6 cubic meter debris volume with a single flexible barrier, as well as with the upstream barrier to compare them. So let's focus on the last 2 tests because they were a similar volume, and then we can see the effect of flexible barriers. Various observations were made in terms of flow depth and flow velocity, and the results were compared. But before that, I can show you one video of of the test. Here you will see a video where you'll see release gate on the left side, and the material will run from left to right. It's an aerial video. Here you see the fixed bed, erodible bed, and runout zone at the end, terminal flexible barrier. And when materials are released, and then finally it stops at the end. And this is a video from V6 B1 where only terminal flexible barrier was used. We measured erosion in the entrainment zone by measuring how many nuts were removed due to erosion process. And we were able to measure how much is the entrainment depth for each test. The major conclusion is this: the higher entrainment happens at the start of the erodible bed. Higher initial flow volume also means higher entrainment, meaning that if you had more debris flowing on erodible bed, so it was more entrainment. And when we have upstream flexible barrier, in case of third test, V6B2 as a green colored line and red square symbols you see, they are for upstream flexible barrier, and it reduces entrainment. Just to just to compare these last 2 tests, that as you see here, the orange color line, which is without upstream flexible barrier, where entrainment depth was almost 108 millimeter for first 4 meters, compared to test with upstream barrier, where the entrainment was less than 60 millimeter, and it went almost close to 0 as we went further in the entrainment zone. We also could see that entrainment rate was very high when we did not use upstream flexible barrier. So what is happening at flexible barrier itself? It was interesting to observe that when we had upstream flexible barrier, there was a curved overflow of debris mass, and it has impact on design principle for upstream flexible barrier. I'll come back to this. We also looked at the stresses at the base of debris flow to see the impact on the upstream flexible barrier. When we had no barrier, in the test V6B1, when we had no upstream barrier, the basal stress were measured, and it was compared with the test with the barrier. And we can easily see that the normal stresses was very high nearby the upstream flexible barrier, and that was due to centrifugal stresses induced by the curved flow path. What happens with the terminal barrier? When we don't have upstream barrier, then we see very high run-up, whereas when we have upstream barrier, we do not see much run-up of debris flow. It also means that when you have very high run-up, it will also induce very high impact force on flexible barrier, whereas upstream barrier, test with upstream barrier will have very limited impact forces. The major findings were like this: upstream barrier decreased entrainment by 70% and impact force on the terminal barrier by 94%. We also realized that when we put upstream barrier, the design dynamic pressure coefficient needed to calculate impact force was decreased from 1.2 to 0.2. What it means that upstream flexible barrier not only reduces entrainment, but it will also reduce impact force. It also means that we can actually optimize the design of terminal barrier if we use upstream flexible barrier. However, when we use upstream barrier, we need to be careful in designing upstream barrier because due to centrifugal forces, there was a very high normal stress observed on upstream barrier, and therefore the dynamic pressure coefficient became 2.2, which is much higher than the recommended 1.5 in design guidelines. So this need to be looked further in and perhaps use higher coefficient for upstream barrier. And furthermore, studies needed to understand the impact of debris and depending on how is the maximum deformation and orientation of flexible barrier. I'll go to the next topic, which is non-structural countermeasure. As the structural countermeasures are expensive, so sometimes we have to rely on the non-structural countermeasures, or perhaps combination both is the best. When we talk about non-structural countermeasure, it is about early warning systems. Early warning systems can be two types: regional early warning systems or local early warning system. I'll talk about regional early warning system. Usually it's given for large areas, and usually it is based on empirical methods. Early warning system exists all around the world, in Asia, Europe, North America, South America. In Norway, we have Norwegian Water and Energy Resource Directorate, which is issuing early warning for different landslide types and flooding. In Norway, where we issue a regional early warning for soil slopes in a grid of 1 kilometer by 1 kilometer size. And this is based on a simulation of water balance. What it means, we look into how much water supply is done due to snow melting and rainfall to the soil, and what is the soil saturation percentage already. So if we have a soil is very saturated, let's say 80, 90%, then it can need a little bit of water supply, and then it will be having higher chances of getting landslide. So we use very simple technique, how much water is supplied through rainfall and snow melting to the soil, and what is the initial saturation level. And we have 4 levels of warning system: 1, 2, 3, 4, where 1 is green color, safe, 2 is landslide possible, 3rd level called some large and smaller landslides are expected, and 4th is large and small landslide expected, and we need to be prepared for quite many landslides, which can affect infrastructures and also cause damages to environment and risk lives. And we have a website called XGeo, where we issue early warning. First warning comes 72 hours in advance, and thereafter it becomes more precise, 48 hours and 24 hours in advance, and then we can issue warning in the area where there's a chance of landslide and so forth. But usually this kind of warnings are given for a large area. And the areas can be very big, in order of 10 kilometer or 10 by 10 kilometer or 100 kilometer by 100 kilometer. And if we look into resources available at the county level, we need to always think, how can we even better prepare us by allocating our resources and emergency response to the right location at right time. We need to have even more accurate early warning. So how can we do that? Perhaps we can think beyond what we do today. Perhaps we need to incorporate landslide susceptibility maps. We need to incorporate the climate models in the current early warning system. That was the motivation for another PhD study, which was conducted recently together with Norwegian governments, agencies, and research institutes, meteorological department, as well as some technology provider. Topic was related to quantification of climate change impact on rainfall, induced shallow landslide susceptibility. This topic has been studied quite a lot around the world for different type of landslides, but also different climate abnormalities. Several studies investigated the effect of climate change on landslide susceptibility by employing a physical-based model with rainfall event downscaled from global circulation model to regional climate models. To the extent of our knowledge, none of these above-mentioned studies attempted to investigate overall climate change impact but mainly investigated only rainfall events of different return intervals, especially extreme rainfall events of long return intervals. However, considering only extreme rainfall events with a low probability of occurrence may overemphasize the climate change impact on landslide susceptibility. So this is something to be aware of. So we developed one new modeling framework where we, in fact, integrated climate modeling chain with landslide modeling chain. The climate modeling chain was based on the emission scenarios, and we chose emission scenario RCP 8.5, which is a pathway delivers a temperature increase of about 4.3 degrees Celsius by 2100 related to pre-industrial temperature, and RCP 8.5 is a worst case scenario. We chose that. Change in the climate were calculated based on dynamically downscale climate model data, historical observation of precipitation. For that, we needed a general circulation model, which was downscaled to regional climate models and also account of local atmospheric phenomena. The purpose of getting this regional climate model was finally to deduce intensity, duration, frequency curve for future climate conditions by utilizing future climate projections by Eurocodex assembled combined with the present climate condition. Eurocodex domain is the European branch of the International Codex Initiative, which is a program sponsored by World Climate Research Program to organize an internationally coordinated framework to produce improved regional climate change projection for all land regions worldwide. Through this climate model, we were able to estimate, we were able to generate IDF curves, intensity, duration, frequency curves, which was used together with landslide modeling chain. The landslide modeling chain was a physical-based model where we used transient rainfall infiltration and grid-based regional slope stability, TRIG-RS, a very well-known model. The effect of climate change on landslide susceptibility are investigated by simulating rainfall events with varying duration and intensities based on the IDF curves from climate modeling chain. So IDF curves were provided by the climate modeling chain. It was supplied to our TRIG-RS model to obtain landslide susceptibility. IDF model, so IDF curves were generated using the equation as you see on the screen. You can read the details. This simple equation was, which is a semi-empirical equation, was suggested by the Norwegian Meteorological Institute in the publication Benestad et al. In 2019 and 2021. So basically, we have climate-dependent IDF curves, which is to be used in landslide modeling. To test this framework, we chose one case area nearby Trondheim, a large area, where we generated IDF curves based on the regional climate models, and we divided the time periods in three: present, near future, and far future. Present is 1981 to 2010, and the near future 2021 to 2050, and far future 2071 to 2100. In this area, Hegra, as you see on the screen, there we have data observations from 1895. So we had sufficient number of data to make a good study of what has been happening for past 140 years, and that was used for projecting future scenarios for rainfall events. We studied the area for the soil type, the previous landslide events. Those landslide events were studied, back calculated to calibrate the model. Once calibration was done, the IDF curve, which we obtained through the climate model, was used to calculate overall probability of landslide initiation at a given rainfall duration. You see on the screen, rainfall duration 12 hours, and For that, results will look something like this. For present, near, and far future, you see 3 different plots for the landslide susceptibility map. They look similar, but if you go into details, you will see, depending on different soil slope range, how the probability of landslide will change from present, near to far future. And we can see increase in probability of failure in the future for this area. In addition to that, we also saw the area itself as how large area can be susceptible to landslide in the future. And you can see here, there are some details, but as you can see, if you look into these 3 green pillars where we put the limit of 20% for probability of failure. So we see that the area which will be prone to landslide will increase in the future. It means larger areas can be subjected to landslide. The major finding from this study was that yes, climate change will affect a landslide, and probability of failure will increase, and it can increase to 10 to 4% depending on rainfall interval we choose. If we only look into extreme weather events, the probability of landslide failure for this area will increase by 27% for 10 years return period for 12 hours duration. This study was probably the first attempt to integrate climate model into landslide susceptibility assessment by considering multiple rainfall events with their corresponding likelihood occurrence in a probabilistic framework. And the proposed integration framework shall lead to more accurate detection of critical zones with a higher increase in probability of landslide initiation under climate change. Therefore, a better strategy to tackle upcoming risks can be developed and better preparedness can be achieved. The overall message here is that now we are going towards more dynamic landslide susceptibility maps that can be integrated to offer even more accurate regional early warning systems. I'm coming towards the final part of my presentation, and I'll talk another different topic than the other 2. It's a risk communication using gamification of natural hazard. It's a part of digital transformation projects at NTNU. There are 9 projects being run with 48 PhDs. Around 6 PhDs are working on something called World of Wild Waters, gamification of natural hazard, a transformative way of thinking how to handle natural hazard. As you see on the screen, some numerical simulations which we have done for debris flow. You will understand it. I understand it because we are geotechnical engineers. But when you show all these colorful images to general public or policy makers, decision makers, they don't understand it. And it also means even though we want to communicate something which is very important, we are not able to communicate to them. That is the motivation behind this whole project. How to use digital tools to do better communication. How can we use immersive technologies, advanced technologies to make tools which is dedicated to specific users, to test emergency response plan, and also tools which can be consistent and repeated for training purposes to the first responder without real exposure to the hazard. So using digital technologies for a better risk communication, that has been the purpose. The project had a 6-part where we had to create often realistic data. We had to do realistic simulations of both floods and landslide using virtual reality, creating user experience, but also including human behavior. To succeed in this, we had to have multidisciplinary team. Now currently there are 5 professors, including me, working on this. Hydrologists from computer science, from mathematics, from psychology, from geotechnics, 5 professors together with 6 PhDs working together to develop some interesting tools. There's one paper recently published on visualization of debris type landslide through virtual reality. There you will see a complete methodology for how we can do the visualization. We need different tools to visualize. We need to do our classical numerical simulation, but as well as we need to think of post-processing of the data to bring virtual reality setting. In a simple way, I can put them in this format, which is more easy to understand. Topographic database, this is where we start. As geotechnical engineers, we know we need terrain data, DTM, LiDAR, to create terrain information, to create mesh for our numerical simulations. And once we have those mesh information, we can do numerical simulations using different softwares. We need soil parameters to do landslide modeling. To do the modeling, we do lab testing. We need other meteorological data and so forth. This is our typical soil mechanics, geotechnical engineering practice when it comes to landslide analysis. We need terrain information, we need material information, we need a simulation platform. If you want to make a virtual reality based game, so we need to also need 2D information about the BIM, building information. Then we need to have 3D images. It could be infrastructure, it could be buildings. We need to also 3D environment, the vegetation, with if you have some different roads and different objects. They need to be combined with our numerical simulations. Meaning that when we do numerical simulations, we get different results of how landslide is moving, at what speed, where material will be flown. Those material information which we get from numerical simulation need to be tied together with the 3D environment which we generate through BIM model. And these two need to put together. Something comes from geotechnical engineering side, something comes from geodesy side. They need to put together in virtual reality environment to create a good user experience. So here we need to work with a computer science programmers, those who work with geomatics apart from geotechnic. And once we do this kind of numerical simulations, we can bring it further into real virtual reality environments such as this. Here you will see a simulation of the same debris flow modeling which I showed earlier. In a virtual reality environment, is a road, there's a car going, and as you see, this is a debris flow which is coming down the hill. This is a prototype 0, which was made a couple of years ago. And now you're inside virtual reality environment. You can move around and you can see the video from different angles. You can be seeing the debris flow from as a driver for a car, if you're driving from the east or driving from the west. And then you can assess, depending on the speed you're driving, whether you'll be able to stop before you hit the debris or you will end up in debris. More realistic simulations are being done for landslide and flooding. I'll show you the latest one with the flooding. This is creating more realistic virtual reality environment by adding sound, adding more colorful houses and colorful buildings, also sky and so forth. What you see here is a real flood simulation which we do as such in using our two-dimensional or depth-headed software models. And those results which we have from our classical way of doing simulation is embedded in this virtual reality environment. And now this, as you see, it's a real physics-based simulation in virtual reality environment. It is taken further step into a game where you can put some questions to user to answer the question or identify which area is safe to go. You can use this kind of environment for training the first responders so that they know where is the danger and which area is easy to access. So this is a method which is under development, and it's going to be more and more new versions of this virtual reality to come. But these are the results I have for the time being. So future application of this kind of tool will be improved, will be to have better hazard and risk communication to general audience. Also safety and rescue operations training to first responder, those who make decisions. They will be able to see what type of risk we talk about. Also, it can be used in early warning systems, and not to mention in our education and education programs. I will now summarize the presentation. I think the role of geotechnical engineers have evolved from simply calculating factor of safety to work more efficiently towards societal challenge. I think this was said also by Dr. Suzanne Vikas some years ago during her ranking lecture, and I totally agree with her. Whether a landslide hazard, whether a landslide hazard will convert into landslide disaster is up to us to control. Through better design of structural countermeasures, better early warning system, I think we can avoid turning a landslide hazard to a disaster. Early warning systems help to increase the societal resilience against landslide. This is important, and we shall emphasize more and more towards having accurate early warning system, more precise early warning systems. Landslide susceptibility assessment should be dynamic and regularly updated to account for changing climate, so that we are not only having one susceptibility map, which was based on slope angle and friction angle of the material. I think we need to make it dynamic by including changing climate and external factors that may affect the susceptibility. Combining state-of-the-art knowledge from different domains, such as digitalization, as I was showing in the virtual reality environment, IoT sensor technologies as such, opens new possibilities to conduct risk assessment and risk communication effectively. With this, I will close my presentation, and I think I've used my time. Thank you very much.
So much. That was fascinating. A very, very, very interesting presentation. I really like, I mean, you covered a lot of different grounds. So yeah, you stated that